Our next speaker is Coline Devin, who's here from Berkeley, and she's going to talk about robotic learning and manipulation, simulation, all sorts of interesting things. Here, Coline.
All right, hi everyone, I'm Coline, and this is going to be a very different application than we've seen before. No biology, only things that are not alive ever. So I'm interested in robotics, and I'm interested in having robots that can interact with the real world and leave a nice closed lab and go into a new space with lots of things in it that it's never seen before. And thinking about how is a robot going to be able to deal with the extreme diversity of things in the world. Because we have these data sets that have nicely labeled bounding boxes around, water bottle, chair, airplane, computer, the common objects in the world. But the number of little baubles, things that we can describe and we can think about as humans, but that are just not present in the current data sets. So thinking about how we can incorporate that into a robot interacting with the world. So as humans, we perceive the world in a nicely structured way because we've had a lot of data that comes in through our eyes, and we're able to make a lot of inferences without needing to use a lot of experience in every single situation. So this was a paper from some other people at Berkeley looking at human priors, and if you think of this platformer, well, it'd be pretty easy to understand what you're supposed to do. You can go up ladders, you can pick up keys open doors, that's all very logical. But for a computer that doesn't know anything about human priors, the computer doesn't know that the black pixels next to a gray pixel behave the same as black pixels next to other black pixels. And it doesn't know that doors are doors. And it doesn't necessarily know that the pink thing here behaves the same as the pink thing there. And so these folks at Berkeley tried to remove all these priors from how we see the game and give it to a human and try to have the human to play this horrible gobbledygook version. And humans were very bad at this. Humans were much better at the version that agrees with what we're used to seeing. And so, but the computer doesn't get all these priors yet. It has to actually play the game in order to learn all this information. And so we kind of have to think in the mind of the robot, what does it actually know yet? And the answer is usually not very much. And so my videos got untrimmed, so you'll just have to bear with the rearranging of the camera every time. But so here I trained a robot to pour almonds into this brown mug, and I put the mug in different positions, and the robot learned to pour into the mug. But and this was learning end-to-end from pixels, so you just have an image, and it's trying to do the right action. And so to the robot, it's actually just looking at a brown blob of pixels. It doesn't know that this is a mug, doesn't know this is a table, doesn't even know it's holding a water bottle. All it knows is that there's some brown blob in its image, and the motions of its arm are correlated to the position of the brown blob. And so as a human, obviously we know how to pour into a brown mug. We also know how to pour into a pink mug. But when the robot is faced with a pink mug, well, the pink mug is not a brown blob, and so therefore the robot is going to just pour somewhere. The average of all the positions it's seen of the brown mug, something like that. So this is not very useful to us, but it's obvious in hindsight that the robot doesn't know anything about mugs. And so instead, we can take a step back, maybe end-to-end from pixels. This has limitations because it has to learn everything from whatever supervision you have. So this is some follow-up work we did in driving. We're thinking about how can we incorporate all the information that people in computer vision have been working on for a long time, which is we know that objects exist. People have written object detectors, and they work pretty well. And so if you just give the robot this unstructured pixels of the street, and then you give it labels about what actions it should take, drive forward, drive right, it has to learn about cars, it has to learn about pedestrians, it has to learn about lanes, all from that one piece of information that you gave it. And so it's going to take a lot of data. And so you can do something a little smarter, maybe have it choose what area of the image it looks at, so you can throw away already a bunch of pixels that the model has learned as useless. but still just takes a lot of data. Or you can run an object detector that has been trained on people putting boxes around cars, putting boxes around people, and you can detect these objects, and then you can give that to the car. And maybe you want to also give it these pixels in case you miss something. So you're detecting cars, but maybe you're not detecting streetlights, or you're not detecting lanes. And so you could give it both this information, and now suddenly the car doesn't need to learn to detect cars from action labels, and instead it can just use that directly. And so we can think of this as like a sort of direct transfer from vision. You train on your vision data set, use that on the image, detect an object, and then you can try to learn the control from the position of the detected objects. And so this works in driving because detecting cars, detecting pedestrians is a well-solved problem. It transfers pretty well, at least in our experiments. And you can also give it the features of the whole image and do deep learning on that, and then predict the action. And this performs better. Right, and we had some experiments in GTA and in some real-world data set. And you can see that it chooses which objects to look at. But in the manipulation world, we end up with a problem, which is that since we don't just have cars and pedestrians, now we have a large variety of objects that don't even have names. And most of the time, you're going to be quite lucky if it detects the thing you want it to, and most of the time, you're not going to be lucky. So if you train a model on MS Coco, and you run it on your robot's camera, well, oranges are an MS Coco, so it'll label your orange. And spoons are an MS Coco, so it'll label a spoon. But a dustpan, that's not an MS Coco. So it'll do its best guess. Maybe it's a spoon. But now if you want to use spoon to find your dustpan, then if you put another spoon in the scene, it's going to be really confused because the spoon looks more like a spoon. And your robot is scissors. What else do we have? We've got your Kiwi plushie is a sports ball. Teddy bears are pretty good. We've got a chair here. Basically, you don't know what you're going to get because these are out-of-distribution images. They have robots in them. No data set has robots in them, so it gets confused. But this was still a lot of useful information. It still knew approximately where objects were, just didn't know what to call them. And so we'd still like to be able to use that information while being able to adapt to new objects during your training. And so we did something pretty simple here. This was a couple years ago. We were like, OK, well, we can take an object detection network that first predicts bounding boxes and then tries to label them. And then we just drop the part that labels the bounding boxes and just keep the class-independent bounding boxes. So we can run this on a robot camera, and it works pretty well. I'll draw a bunch of boxes. And so even though it draws a bunch of extra boxes, we don't really care, because at least we've already dropped a bunch of pixels. So when we were doing end-to-end from pixels, it had to learn to deal with the table, to learn to deal with the lighting, all of that. Well, now we don't really look at the table anymore. We're already looking at a smaller number of things. And so we'd like to be able to take this, and then for this task, which is obviously to sweep an orange into a dustpan, we'd like to be able to identify that the orange and the dustpan are the important things, and that your action should just depend on those objects and not really anything else. And so the method that we use is we use a demonstration data to learn which objects you care about. And then we run an RL method called guided policy search to learn to output the right actions given the object position. And then we'd like to be able to generalize seamlessly to robustness. So a different mug shouldn't break the policy. So for example, here are some demonstrations of the task. So I'm showing the robot a couple different things. And here, this is the scale of like a handful of demonstrations. I think we use 6 demonstrations of the pouring task. So a very small amount of data. And then from the demonstrations, we now can process them as a set of objects instead of just a list of pixels. And each object has to now be labeled with some features. Because the boxes are going to be in different orders every time, we can't just put all the boxes into concatenated into a network, we instead want to choose an object. And we don't want to choose an object based on its class label, because class labels are not very trustable. And so instead, what we do is something very silly, which is we just take a network that's been trained on ImageNet, and we chop off the top, and we pass the crops through it, and label them with some features. And it doesn't really matter what these features are, but the features are going to define how robust you are, or how general you are, and how much you might be liable to be distracted. So right now, this was our first approach at this. So we just passed it through some ImageNet network, get some features, and now we have a set of boxes that are labeled with a feature vector. And so now we just need to figure out a way of choosing which features are the ones that we care about. And we can do this in a end-to-end. I don't know what that means anymore. We can do this, but with learning, using our demonstrations. And so if you think of your demonstration, we've got a frame, and it's labeled with an action that was taken in the demonstration. And so we can pass each object through our network to get a feature vector. So we got a box position and a box feature. And now we can implement the attention. So we instantiate a attention vector W, which is supposed to choose one of the boxes. And so we initialize it randomly, and then we take its dot product with each feature vector of the different objects and do a softmax. And so this is your attention map over the objects. If you know your task is going to use more objects, you'll have to instantiate more attention vectors and do each of them. And then to learn the W, we just try to predict what the demonstration did and backpropagate that through the attention vector W. And we don't backpropagate through the box features in this case, because we're doing this in a really small data set. If you had a large data set, you could learn everything together over many tasks, and then it would be much more clean, I guess. And so with this task-specific attention, we basically get to choose our objects. And then running the RL is really easy because let's see. What happened to my videos? OK. Anyways, so running the RL is easy because it's a very low dimensional state space. It's just the position of the box. And as you see, the robot can now generalize to clutter, pink mugs, different background colors, because the features from the ImageNet model are quite consistent and are invariant to the things we care about, because they've seen a lot of images, they've seen a lot of human labels that are semantically meaningful. And so we can leverage all that data in our robot application, even though the actual ImageNet task is a very different task from the robot task. And so this works on tasks with 2 objects. It can ignore the other orange blob of pixels because it's using a network that can recognize oranges at some level in the feature space. And so this is nice because the features gives us more flexibility. And then we can use the object positions, so we get efficient policy learning. And the object representations can generalize pretty well across object classes, or be robust to different lighting conditions, be robust to different background colors, and all the things that we would like to take for granted, but that do really affect robots when they're trying to perform tasks. However, we are really dependent on those pre-trained features. And where they come from and what data set they were trained on is going to affect all of those results. And so here's another picture. I just love doing this. I love taking a robot picture and then running it through a pre-trained network and seeing what happens. So here's another robot, and it's holding, I think, a lock and some weird yellow rubber thing. And so this is very confusing to the network. It thinks the robot is a vase. It thinks that there's a toothbrush in here, a dining table. I don't really know. And so in this is a different data set. So here the ImageNet features actually didn't work very well because we were looking across different viewpoints. So even though from one particular viewpoint, the image features of an object might be consistent over time, from different viewpoints, they aren't at all because their scales are different. And so if we take this, we have this image of a glue stick, I think. And so if we look at the features of this glue stick, and we try to find what point in this other image, the bottom image, where is this, what pixels in this have the most similar features to the glue stick image, it's not at all correlated to the position of the glue stick in the image. So these objects don't have the same features at the different viewpoints. And so how can we, instead of relying on these data sets that might not generalize at all to our situation, it'd be cool if the robot can actually learn these representations using its own experience. So some prior work that has used this idea of learning from your own experience. So at Google, they got the robot to learn to grasp just by trying to grasp over and over again and automatically labeling whether or not a grasp was successful. So here, you don't need to have humans label the success function. You can just kind of write a heuristic, like in the previous talk, and optimize that. And so with this self-supervised learning, where you don't need human labels, then the robot can actually provide a lot of its own supervision. And another approach of trying to learn object segmentations by having a robot push objects around. And because here, the robot, by interacting with the real world, the laws of physics apply. This is the real world. And so you know that if the robot is pushing something or is picking something up, then that has to make a change in the environment. And we can use that predictable change to learn where the objects are, what their boundaries are, and things like that. So in this case, this was some work I did at Google last year. We noticed that just a simple grasp provides you with a lot of information. So if you know that you have successfully grasped an object, you know that the object is currently in your gripper. That's where it has to be. And if it's in your gripper, that means it used to be in the scene. You didn't grasp it from nowhere. You grasped it from the scene in front of you. And obviously, since it's in your gripper, it's no longer in the scene. So now just by having a robot grasp something, it doesn't know what it grasped, but it does know that it has 3 images, and the object is in 2 of them, and it's not in the last one. Or there could be another object of the same type in the last image, but that means there must be n+1 objects in the scene before you grasped. So you kind of have this arithmetic structure. And we actually use this supervision to learn a representation of objects. And we use something kind of a little funny, which is that we say that if we have some representation space of images, the representation of the scene before you grasped, where there is n+1 objects, minus the representation of the scene after you grasp, where there's obviously n objects because you've grasped one, and then that should equal the representation of the object you grasped in your gripper, because that's where the object is. And using this objective, your scene has to be embedded as a set of objects. Your representation has to be some transformation over the representation of, you have 2 bottles, you have 1 blue cup with these words on it, and you have 0 plates. And then your features also have to be viewpoint invariant, because the position of the object in the scene is going to be different from the position of the object in the gripper. And you also have to be spatially invariant, because the other objects move during the grasp. So here you can see the blue cup rolled in the bin while the robot was grasping the bottle. And to leverage this objective even more, we actually use a special architecture, which is that instead of doing your standard convolutional, flatten, fully connected, we do a fully convolutional embedding. So instead of having a single feature vector by using a flattening, we simply sum over the spatial dimension of the feature map. And this will give us the spatial invariance for free. And it'll also preserve the feature embedding in the spatial feature map. So we'll see why that's useful later. And so we embed all 3 of these images, and we use our objective function, which is a triplet style loss, where the subtraction of the 2 embeddings that we know of the scene should be close to the embedding of the grasped object. And it should be far apart from other images that are in the same training set. And so the first task we're going to use this for is to do goal condition grasping. So I showed you grasping earlier, where it was just supposed to grasp anything. It was rewarded for grasping something. And that's an easy problem to supervise, because you can just use some heuristic function to say, oh, something is in your gripper. Instead, we want to be able to grasp a particular object. So for example, here we've got we want to be able to give the robot a goal image, for example, of the blue. Here's the goal image of the blue Lego block, and the robot should pick up the blue Lego block. So the problem is that we need to be able to have some success function in order to train this policy in the real world. And so how do we know if it's grasped the correct object? Well, we have these nice feature vectors that are supposed to differentiate objects and tell you if two objects are the same. And so we'll just take that. So you had some goal image, and we can embed it. And then there's the image of the object it actually grasped, and we can embed that. And then the reward is just the cosine similarity of those two embeddings. And so if we can train this using reinforcement learning, because this is a reward function. And so we train this in simulation first. And so in yellow, we've got the success at grasping the correct object of objects that were seen during both the representation learning part and the grasping part. And then in blue, we have a holdout set of objects that weren't seen during either representation learning or grasping. And we can evaluate how good it is at grasping those given an image of the object. And so we can see that here on the farthest on your left is the oracle label. So in simulation, we can actually say, you grasp the correct object. That's easy to label in simulation. And then on the right, you've got the version where it's labeled using our function. And so actually, our version generalizes better to new objects. Because instead of just being 1 or 0, correct object, incorrect object, you get a little bit of smoothing. Oh, you grasped an object that's similar to the one you're supposed to grasp. And so that helps it learn a little bit more general of a policy. And so we can actually grasp new objects better. So as I mentioned, the spatial feature map is going to come later. So there's something cool that we can do because we have, instead of just having one vector for the whole image, we actually have an embedding per pixel. And so what we can do is that we can embed an object image and then take its dot product at each pixel location in the scene image. And because these embedding spaces are the same, similar objects are at similar vector positions, then we get a localization of an object within a scene. So this works. So if you look at the bottom line, the red dot indicates the highest similarity position of that dot product. So we can just find objects. And then we want to do this in the real world. So in the real world, we've got a large diversity of objects. I think we have 500 different objects, totally random, pretty weird stuff. I don't really know who picked this object set, but this is what we had. And this localization property works there too. And so these are on unseen objects. These are objects that weren't seen during the representation learning, but it's still able to localize them because the representation is robust to different viewpoints and things like that. So you can localize a rubber dinosaur. You can localize an eraser, a blue marker, whatever you want. And so now we can do real-world goal condition grasping. And instead of having to rely on reinforcement learning the whole way, we can quickly initialize it by first localizing the goal object using our representation. Then we just move the arm there and run the grasping policy from there. So here's some examples of that. So if you have this goal image of the yellow cup, it goes to it and grasps it. And the outcome similarity, so this is the similarity of the representations, is about 0.79. So that's high, so it's marked as correct, and it moves on. You've also got this brush. This one's a little harder because the brush is under stuff. So it first starts grabbing things near the brush and notices that the similarity isn't good enough. So it keeps trying until the correctly has the brush. And so here we've got some takeaways that the robots actually can learn to represent objects just by interacting with the world. And that the interaction itself provides a ton of supervision, one that we're used to using all the time without really thinking about it. I pick something up, oh, now I know it's heavy. And so because robots have that capability of taking actions, leveraging this is a great way to add more labels to your data and really be able to predict the world in an easier way than the more traditional ML approach where you have a fixed data set and then it gets labeled by experts. And also that by interacting, you really do get a sense of objects because objects are things that move together. And a single image of a scene doesn't tell you anything about objects because it's it's static. But once you get dynamic, that's really where objects come out and are really natural abstraction for robots.